Alright, we have another variety of ODE. This time we'll be studying what's called a linear ODE. Now when we're looking at a differential equation and we're trying to figure out what type it is, one of the useful ways to classify a differential equation is by something called its order. The order of a differential equation is the order of the highest order derivative in the equation. For a quick example, let's consider the two ODEs down below. In the first ODE, we have a second derivative, a first derivative, and the original function y. In this case, the highest order derivative is the second derivative, y double prime. So this diffie would be considered to be second order. Whereas in the second example, the highest derivative that we have is a first derivative, and therefore this would be a first order differential equation. So in this first part of the course, we'll be focusing mainly on first order differential equations. Slope fields, for example, were things that could only be drawn for first order differential equations. Y prime equals a function of x and y. Separable ODEs, and thus autonomous ODEs, were special cases of first order differential equations, so that is our focus for mainly the first half of the class. And we'll be working on second order differential equations in more or less the second half of the class. Now if you have a first order differential equation, then that can be called a linear under the following circumstances. A first order differential equation is called linear if it can be written in the form y prime plus some function of x times y equals some function of x. Once we get to talking about mixing problems, which we'll introduce for the first time tomorrow, problems that involve mixing two different chemical substances, those problems very often are represented by linear differential equations. So are a lot of temperature problems, Newton's law of heating and cooling. That's also represented by differential equations that are linear. So today we'll get a chance to see how these kinds of equations are solved. So the technique that we will use to solve differential equations that are first order linear is called the integrating factors method. So I'm going to spend a little bit of time just explaining to you where this method came from, where it arises, why we're doing this. If you don't care about that, you're free to skip to the next timestamp, but I do find that when students see the derivation and see why this method is used, it can make the method a little bit easier to remember. So I recommend just viewing it once if you have the time. We're going to try and find a solution to the linear ODE y prime plus p of x times y is equal to f of x. And I'm going to define a new function of x, which I will call u. The books call this mu, the Greek letter mu, which is u with an extra long tail. I'm not going to be bothered, I'm just going to call this a regular old u. We're going to define this integrating factor in a kind of strange way. We're going to take the exponential e, and then in the exponent, we're going to put the integral of the function p of x that appears next to y in our linear differential equation. Now notice something. If we take the derivative of the function u here, what do we get? The derivative of the function u can be found by, first of all, chain rule. Chain rule which says, first of all, copy-paste your e to the something, that by the derivative of that exponent. But when you integrate a function and then take its derivative, those two operations are exact opposites. So u prime is equal to just p of x times e to the integral of p of x. Put another way, u prime, if you take the derivative of u of x, you just get p of x times your original function. Okay, interesting. So now what we're going to do is we're going to consider the derivative not of just u, but the derivative of the product u times our solution y. What happens if we take the derivative of this product? Well, then product rule says that this is going to be equal to u of x times u prime plus u prime times y. And we also know that u of x from the above line is equal to u of x times p of x times y. Now, what happens if we factor u of x out of this expression? We get y prime plus p of x times y, which, amazingly, is the exact same thing as what we had on the left side of our differential equation, y prime plus p of x times y, which means that it must be equal to this function f of x on the right side of our differential equation. So I can rewrite this as u of x times f of x. So what have we discovered? We discovered that if we define u of x in this way, take the derivative of u times y, then that's going to be equal to u times f. And so, as a consequence of that, if I integrate both sides, it'll cancel the derivative on the left, and I get u of x times y is equal to the integral of u of x times f of x. Get rid of the derivative on the left side by integrating both sides with respect to x. So what, therefore, is our solution? What, therefore, is y? Y can be found just by dividing both sides of this fraction by u of x. So, let's sum up what we just derived. If you want to solve a linear ODE, this is how we do it. The first thing that you want to do is you want to find the so-called integrating factor, which I am calling u of x, and this can be found by taking the antiderivative of p of x and putting it upstairs as an exponent on e. A note, when you do this, you don't have to worry about the plus c in this integral. Everything will work itself out, even if you ignore it. The second thing that you want to do is you want to set up the equation u of x times y is equal to the integral of u of x times f of x, where f of x is equal to the function of x that is all alone on the right side of the differential equation. Once you've set up this equation, you're going to want to go ahead and evaluate this integral on the right side. And this is the moment where plus c actually will matter. Finally, once that's done, the only thing that you need to do to actually find y is to divide both sides of the equation by the u of x on the left side in order to get rid of it. Memorize the equation for the integrating factor and memorize this equation in pink here. As long as you know these two equations, you can usually find your way to the end of the problem pretty well. Now, just a warning, if you are going to use the method of integrating factors, you need to make sure that your linear ODE is written in the correct format. It needs to be written in this exact format, y prime all by itself, plus a function of x alone, times y equals f of x. This is the only way that you are going to know the true and actual values of the functions p of x and f of x for these calculations. Let's begin with a very simple example. Let's solve the ODE y prime equals x plus y. The first thing that I need to do is I need to get it into the correct form. Currently, this is not in the correct form because I need both y prime and y to be on the left side of the equation. So I'm going to subtract y, which is equivalent to adding -1 times y. So now that I've gotten my ODE into the right form, I can see that the function that contains no y's, the one that we're calling p of x, is -1 in this problem, the constant function -1. And the function on the right side, containing only x's and no y's, we call f of x, is equal to the function x in this case. So, step 1, I'm going to figure out the value of my integrating factor. So I'm going to figure out the value of e to the integral of -1. The integral of -1 with respect to x is just -x, and since I'm just finding the integrating factor u of x, I don't have to worry about plus c here. I can use the simplest possible antiderivative of p of x. So now that that's done, I'm going to set up the equation u of x times y, so e to the minus x times y, must be equal to the integral of u of x, e to the minus x, times x, which is the function f of x in our problem. Now let's go ahead and evaluate this integral on the right-hand side. This looks like a prime opportunity for integration by parts. If I set v equal to x so that dv is equal to 1, and du to be e to the negative x, so that u is equal to negative e to the negative x, then integration by parts says that the integral on the right side is equal to u times v, so negative x e to the minus x, and then minus the integral of dv times u, so negative e to the negative x. So if I integrate that, I get e to the negative x times y equals negative x e to the minus x, and then 1, 2, 3 minus signs, minus e to the minus x, and this is where we need to remember the plus c. So finally, let's go ahead and let us solve for y by dividing both sides by e to the minus x. So that will cause y to be equal to negative x minus 1 plus c divided by e to the minus x, which, if we so desire, can be rewritten as an e to the positive x in the numerator. The solutions to the given linear ODE have this format. If we're feeling skeptical, we can always check. If we calculate y prime for this formula, then we're going to get a minus 1 plus c e to the x. And if we calculate x plus y on the right-hand side, then the x and the negative x will cancel out, and I get the exact same thing, which is negative 1 plus c e to the x. So functions of this format do satisfy the conditions specified, and these functions are the solutions that we were looking for. This is the method of integrating factors. Let's try it again. Let's solve the ODE dy over dx times x plus 2 times y is equal to 3. First, we need to get this into the correct format, which means in particular that we need to make sure that nothing is being multiplied by our y prime. So first, I'm going to divide out that x. Y prime plus 2 over x times y is equal to 3 over x. In this case, our p of x is 2 over x, and our f of x is 3 over x. So let's get our integrating factor. The integral e to the integral of 2 over x dx. I'm going to pick whatever antiderivative I please, so 2 natural log of x, no plus c, no absolute value, which can be simplified if I rewrite this as e to the natural log of x and move the square aside. Now the e and the natural log can cancel, and this is equal to x quantity squared. And so our integrating factor is just x squared. So now that we have our integrating factor, let's set up our general equation. X squared times y is equal to the integral of x squared times the function f of x from our problem. So x squared times y is equal to the integral of 3x. X squared times y is equal to 3 over 2x squared plus c. So now, to solve for y, let's just divide everything by x squared, and we get 3 over 2 plus c, x to the negative 2. You could also write this as c divided by x squared if you prefer. All of these solutions to the linear ODE are of this format: 3/2 plus some constant times x to the power minus 2. This concludes today's material. We talked about linear ODEs, how to recognize them, and a technique for solving linear ODEs called integrating factors.